According to the 2020 National Electrical Code, sharing a common isolated grounding conductor for 3 isolated receptacles can be a proper installation. The key to understanding this lies in properly interpreting and applying sections 250.146e and 250.146f of the National Electrical Code. Section 250.146e addresses scenarios where conductors of different systems are installed within the same enclosure, raceway, or cable. The code dictates that these conductors should not be installed together unless they are isolated by suitable barriers. This requirement is put in place to prevent unintended interactions or fault propagation between distinct electrical systems. Now, turning our attention to section 250.146f, we find an exception to the rule established in 250.146c. This exception applies when conductors of different systems are installed within a raceway. It specifies that in such cases, the raceway itself must be grounded, and the conductors must be separated by a barrier. Let us now consider the scenario with 3 isolated receptacles, each fed by a separate 10 American wire gauge conductor sharing a neutral, and a 10 American wire gauge grounding conductor installed to ground the metal boxes and raceway. If the grounding conductor serves as the barrier between the conductors of the 3 different systems, and the grounding conductor is installed in the raceway with the other conductors, and the raceway is grounded, then the installation can meet the requirements of sections 250.146c and 250.146f. It is important to define what an isolated ground receptacle is. An isolated ground receptacle is a receptacle where the grounding terminal is purposely isolated from the receptacle mounting strap and the electrical box it is mounted on. The purpose of the isolated ground is to reduce electrical noise from affecting sensitive electronic equipment connected to the receptacle. The green grounding wire connected to the isolated ground receptacle runs all the way back to the electrical panel and connects to the grounding bus bar there. This provides a dedicated grounding path for the receptacle, minimizing the risk of noise or interference. The metal boxes and raceway are grounded through a separate grounding conductor that is connected to the grounding bus bar and the electrical panel. This ensures that the metal boxes and raceway are properly grounded, providing a safe path for fault current to flow back to the source in the event of a ground fault. Therefore, when installing isolated ground receptacles, it is important to follow all applicable code requirements, including those related to grounding and bonding. Failure to do so can result in a dangerous electrical installation. Firstly, you need to ensure that the isolated grounding conductor is properly sized. Secondly, the conductor should be connected to the grounding bus bar in the electrical panel. Thirdly, the metal boxes and raceway should be grounded through a separate grounding conductor. By following these steps, you can ensure that your isolated ground receptacle installation is safe and effective. When implementing isolated grounding systems, remember that the goal is to minimize electrical noise and interference. Keep in mind that isolated grounding is not a substitute for proper grounding and bonding practices. It is an additional measure that can be taken to improve the performance of sensitive electronic equipment. Always consult with a qualified electrician or electrical engineer to ensure that your isolated grounding system is properly designed and installed. Grounding and bonding are critical for electrical safety and equipment protection. Proper grounding provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to operate and clear the fault. Bonding ensures that all metal parts of an electrical system are at the same potential, reducing the risk of electric shock. Always adhere to the requirements of the National Electrical Code and other applicable standards when designing and installing electrical systems. This includes proper grounding and bonding practices, as well as the use of appropriate overcurrent protection devices. Regular inspections and maintenance are essential to ensure the continued safe and reliable operation of electrical systems. Look for signs of damage, corrosion, or loose connections. Also, testing of grounding and bonding systems should be performed periodically to verify their effectiveness. It is worth mentioning that there are different types of grounding systems, such as the grounded system and the ungrounded system. In a grounded system, one of the conductors is intentionally grounded, providing a reference point for the voltage. In an ungrounded system, none of the conductors are intentionally grounded, which can offer certain advantages in terms of fault tolerance. However, ungrounded systems are less common due to the increased risk of voltage transients and the difficulty of detecting ground faults. Also, consider the impact of harmonics on electrical systems. Harmonics are currents or voltages with frequencies that are integer multiples of the fundamental frequency. They can be caused by nonlinear loads, such as electronic equipment, and can lead to various problems, including overheating, voltage distortion, and equipment malfunction. Mitigation techniques, such as the use of harmonic filters, can be employed to reduce the impact of harmonics on electrical systems. Surge protection is another important aspect of electrical system design. Surges are transient overvoltages that can damage or destroy sensitive electronic equipment. Surge protective devices, or SPDs, are used to divert surge current away from the equipment, protecting it from damage. SPD should be installed at the service entrance and at downstream locations to provide comprehensive surge protection. Power quality is a general term that refers to the characteristics of the voltage and current in an electrical system. Poor power quality can lead to various problems, including equipment malfunction, premature failure, and increased energy consumption. Factors that can affect power quality include voltage sags, voltage swells, harmonics, and transients. Monitoring power quality and implementing appropriate mitigation techniques can improve the reliability and efficiency of electrical systems. Regarding electrical safety, arc flash is a dangerous phenomenon that can occur when a short circuit creates an electrical arc. Arc flash can cause severe burns, blindness, and even death. Protective measures, such as the use of personal protective equipment, or PPE, and arc flash relays can be implemented to reduce the risk of arc flash injuries. Electrical safety training is essential for all personnel who work on or near electrical equipment. Training should cover topics such as lockout-tagout procedures, safe work practices, and the proper use of PPE. Lockout-tagout procedures are used to ensure that electrical equipment is de-energized before work is performed. These procedures involve isolating the equipment from the power source and applying locks and tags to prevent accidental re-energization. Furthermore, electrical codes and standards are constantly evolving to keep pace with technological advancements and changing safety requirements. It is important to stay up to date with the latest codes and standards to ensure that electrical systems are designed and installed safely and effectively. Professional organizations such as the National Fire Protection Association, or NFPA, and the Institute of Electrical and Electronics Engineers, or IEE, offer resources and training to help electrical professionals stay informed about the latest developments in the field. When working on electrical systems, always use properly rated tools and equipment. This includes insulated tools, voltage testers, and ground fault circuit interrupters, or GFCIs. GFCIs are designed to protect against electric shock by detecting ground faults and quickly interrupting the circuit. They should be used in wet or damp locations, such as bathrooms, kitchens, and outdoor areas. Electrical inspections are an important part of ensuring the safety and compliance of electrical systems. Inspections are typically performed by qualified electrical inspectors who are familiar with the applicable codes and standards. Inspections can identify potential hazards and ensure that electrical systems are installed and maintained properly. Electrical maintenance is essential for the continued safe and reliable operation of electrical systems. Maintenance tasks can include inspecting and testing equipment, tightening connections, and replacing worn or damaged components. A well-planned maintenance program can help to prevent equipment failures and extend the life of electrical systems. In addition to the technical aspects of electrical systems, it is also important to consider the environmental impact. Electrical equipment can contain hazardous materials such as lead, mercury, and cadmium. Proper disposal and recycling of electrical equipment is essential to prevent pollution and protect the environment. Energy efficiency is another important consideration. Energy-efficient electrical equipment can reduce energy consumption and lower operating costs. Incentives and rebates are often available to encourage the use of energy-efficient equipment. The National Electrical Code provides specific requirements for the installation of electrical equipment in hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dust may be present. Equipment used in hazardous locations must be specially designed and tested to prevent ignition of the flammable materials. The code also provides requirements for the wiring methods and grounding of equipment in hazardous locations. Electric motors are used in a wide variety of applications, from pumps and fans to compressors and conveyors. Proper selection, installation, and maintenance of electric motors is essential for reliable operation. Factors to consider when selecting a motor include the horsepower rating, voltage, speed, and enclosure type. Variable frequency drives, or VFDs, are used to control the speed of electric motors. VFD can improve energy efficiency and reduce mechanical stress on the driven equipment. They are commonly used in applications such as HVAC systems and pumping systems. Lighting systems are another important aspect of electrical system design. Energy-efficient lighting technologies such as LED lighting can significantly reduce energy consumption and lower operating costs. Lighting controls, such as occupancy sensors and dimmers, can further improve energy efficiency. The National Electrical Code provides specific requirements for the installation of lighting systems, including the spacing of luminaires, the wiring methods, and the grounding requirements. Renewable energy sources, such as solar and wind power, are becoming increasingly popular. Electrical systems that incorporate renewable energy sources must be designed and installed in accordance with the applicable codes and standards. The code also provides requirements for the interconnection of renewable energy systems to the electrical grid. Smart grid technologies are being developed to improve the reliability, efficiency, and security of the electrical grid. Smart grid technologies include advanced metering infrastructure, or OMI, smart sensors, and communication networks. These technologies enable utilities to monitor and control the grid in real time, improving grid performance and resilience. Electrical engineers play a critical role in the design, installation, and maintenance of electrical systems. Electrical engineers must have a thorough understanding of electrical codes and standards, as well as the principles of electrical engineering. They must also be able to use computer-aided design, or CAD, software and other tools to design and analyze electrical systems. Electrical technicians and electricians are responsible for the installation, maintenance, and repair of electrical systems. Electrical technicians and electricians must have a strong understanding of electrical safety practices and the proper use of electrical tools and equipment. They must also be able to read and interpret electrical drawings and schematics. In conclusion, electrical systems are complex and require careful planning, design, installation, and maintenance. By following the applicable codes and standards and using best practices, it is possible to ensure the safe, reliable, and efficient operation of electrical systems. The proper application of NEC sections like 250.146E and 250.146F are very important.